Okay, this talk is about a quantum jump model of option pricing. So as in the last talk, QEF16, stock market data follows this q-variance and the q-distribution. So q-variance refers to the property that the expected variance of log returns x corrected for drift over a period of t follows to good approximation this formula, sigma squared plus z squared over 2, where z is equal to x divided by the square root of the period. And q-variance follows because we're modeling price change as the displacement of a quantum harmonic oscillator, so a larger displacement is associated with higher energy and therefore higher volatility. So q-variance follows directly from this model. And the probability distribution associated with q-variance is a Poisson-weighted sum of Gaussians known as the q-distribution. The Poisson rate parameter is lambda equals 0.5. And the standard deviation for each term is given by this expression, and the distribution looks like this. So it's a bit more peaked, and it has fatter tails than a normal distribution. And there's a couple of different ways of showing that, as we discussed. But now, what can we do with this q distribution? Well, one thing is that we can use it to calculate the price of a call option. And we can also use it to calculate the q-implied volatility, which is the volatility to be used in the Black Scholes model for assuming that this distribution holds. So if we just go through the exercise of doing that, all the calculations, and you find that the q-implied volatility sigma q squared is equal to q squared sigma squared plus 1 minus q squared z squared. So it's basically like a flattened version of q volatility, q variance. And the number q is about equal to 0.95. Okay, so now we can compare three different kinds of volatility. We have the q-implied volatility, which is the number suggested by a quantum model. We have the normal implied volatility, which is the number used by traders. And then we have the payout-implied volatility, or you can call it the market-implied volatility, which is the number which corresponds to average payouts. So that would be like if you just look at the data and you say what would be the right volatility to use so that the price of the option equals the expected payout. So if we go through that exercise and using data here from option price data from 2004 to 2020 for these three different kinds of implied volatility. So starting with the q-implied, the quantum model. So if we create a volatility surface as a function of log price change x, and that's the volatility, and period t is over here. So we get this surface, and then if we just plot it in terms of z, then it's this simple kind of parabolic looking shape. So that's the quantum model. Interestingly, if we do an implied volatility surface using actual data for what traders are paying, we get something that looks very similar. Again, when we plot it in the conventional way as a function of x and t. When we plot it as a function of z, we get something that looks a lot like the quantum model, but it's not exactly the same. There are some differences there. But the overall scaling, the overall shape is very close. And then when we look at implied volatility, payout-implied volatility, as a function of x and t, again we get this same shape. So it's like you're seeing the same scaling, the same overall appearance. When you look at it in terms of z, you get this again very close to the quantum model, but still slightly differences. So basically, it seems like the quantum model is giving a good kind of first cut look at what implied volatility is. It's also giving you a good first cut look at what the payout implied volatility, the market implied volatility should be. Okay, so to summarize the q distribution, which again comes from q-variance, can be used to calculate the expected payout of a call option or a put option, and This q-implied volatility, so this is the number suggested by the quantum model, is quite close to both implied volatility, the number used by traders, and payout-implied or market-implied volatility, which is the number which reflects average payout. So this suggests that markets are in a way following a quantum distribution, and traders are using a quantum model to price options. They just don't know it. For further reading, there's a couple of references here in Wilmott and Journal of Derivatives.